The work comes from the, just essentially the idea that climate is the most influential, what we call top-down driver that determines vegetation distributions. A lot of other things determine vegetation distributions, like interspecies competition and soil. But climate is the big organizer. And in fact, Nate Stevenson published this looking at how nicely vegetation sorts itself out along major gradients. These two here, AET, actual evapotranspiration, which is the amount of water that actually gets evaporated or transpired by plants. And then deficit, the unmet demand for water, which is a really good index of drought stress for plants. It's essentially what they don't have available to them but would like to. So climate really strongly determines vegetation distributions. We know that. We've known that for a long time. And we know that climate's expected to change. So therefore, we should expect vegetation to change. So and here's the some model results from the Ipcc assessment, looking at historical trends in global temperature or land temperature, and then 4 different scenarios or potential trajectories that might take place given different emissions and other forcings. And the fuzz around those lines are actually individual skinny lines that indicate the output from individual global climate models, GCMs. So there's variability among the models for it. That bold line indicates the average across all of those individual models. We call that the ensemble mean, the ensemble of the models. The red line is the forcing pathway, the scenario that we seem to be on track for. So we were curious, okay, so what might this mean? And can we look at what this might mean for vegetation in North American protected areas? So we selected 22 protected areas that are large and are managed either as wilderness or parks, primarily for natural processes. And our aim was to create fine scale, which means 1 kilometer, vegetation maps. 1 kilometer is very fine scale when you get into talking about climate. And we wanted to look at mid-century projections and late-century projections. And then we also wanted to look at what the actual transitions might be between vegetation types. So the approach that we took to do this is called the climate analog approach. And it makes the major assumption that places with similar climate will also have similar vegetation. So you go about doing this by identifying places, locations that currently have climate that's similar to the climate that you're projected to have in the future. And then you find those places, you see what vegetation is there, and then you make the inference that, okay, my site might have this kind of vegetation in the future. So I'll step through an example of doing this on the landscape of focus for this workshop. So the red outlines is the crown of the continent ecosystem. And this red dot there in the bottom third of that graphic is around White River Pass. So that's my site. And if I look up that site on the land fire vegetation data, I'll find that it's described loosely as cold montane forest. And in 1975, its mean annual temperature was 2 degrees, but it's projected to, by 2055, being 5.1 degrees Celsius. So the question is well, it's cold montane forest today, what might it be in 2055, given that the temperature is going to change? And so what we do is we find locations that today, the mean annual temperature is 5.1. And we refer to those as analog sites. So those are our analog locations. So those are those blue dots that run up there. They're not really, I just threw them on that slide. It's just use your imagination. But so we look at those blue dots and we say, okay, what kind of forest, what kind of vegetation is there now? Well, it's western mesic forest. Like, okay, then we say, well, we're going to infer then that White River Pass is going to transition from cold montane forest to western mesic forest, or at least it has the opportunity to do that. So again, in order to create these fine scale maps, that was our aim, and look at these transitions, these potential transitions. We used the land fire vegetation data, the biophysical settings, and we had to coarsen them up a bit by vegetation types, as you'll see if you're familiar with those data. They have much finer classifications. So we reclassified land fire, and we chose 2 climatic variables to use. We didn't use mean annual temperature. We used 2 variables that mean annual temperature goes into these variables, but climatic moisture deficit and evapotranspiration, and they're very similar to the ones that were on that very first slide where I showed you the vegetation sorting itself out along those 2 axes. And for our analog pixels, in order to define what an analog site was, what a blue dot was, is that climate had to be pretty similar. It had to be within a plus or minus 1 millimeter per year from those annual water balance variables on that square root transformed norm. But they have to be pretty close. And then we took the majority vegetation type from those 7 analog pixels. We chose the 7 nearest analog pixels to the focal site that we were modeling. And we do that for every pixel in the landscape, every 1 kilometer pixel. And then for climate projections, we looked at 3 different GCMs, 3 different global climate models. I'm only going to show you the results from one of those, and that kind of represents the middle of the road degree of change among those different model projections. And then I'm going to look at that trajectory, that scenario that that one that was in red that we seem to be on course for. And so if we look at the crown of the continent, our reference condition for vegetation is represented here in this map. So there's a lot of dark green, there's a lot of cold montane conifer forest, there's some western mesic, there's some western dry conifer, there's only a little bit of shrubland that you can see interspersed through here. There's some alpine and barren in gray. And it's basically this. This is the distribution. And then if we use those climate projections to 2055 and 2085, mid-century and late century, you can see that there's less dark green over there on the right, and you can see that represented in these bar charts here. So there's a vegetation shift that is projected. And then we can look at these cool diagrams called chord diagrams and actually see the transition, like what's transitioning to what. And the way you can see that gray arcing arrow here. Let's see if I can just is that a trick? So alpine, this gray swath here that arcs up and over to montane conifer. Oops. You gotta be careful, huh? That is, essentially representative of, okay, this gray area goes to dark green. So alpine transitions to montane conifer. And these two big dark green swaths that come from montane conifer go to largely mesic conifer or dry conifer. So you can kind of look at the amount of change that that represents each of these transitions. And so we did this for all 22 of our North American sites. And two other ones in the Northern Rockies show pretty similar types of transitions, starting with different different amounts, different vegetation distributions. But basically, the story is pretty much the same, very similar. And so across all of our 22 sites, the potential redistribution of vegetation that we have is alpine shifting to some form of conifer forest, cold montane shifting to mesic or dry forests. Those were the two major ones that we saw in the conifer continent. And then as we go down, similar transitions but involving different vegetation types, and getting pretty complex depending on the protected area. What I want to make a point, though, is that these shouldn't be interpreted as actual vegetation shifts, because that we know that we should expect a high degree of inertia to change. Things are going to happen very slowly. There's a lot of inertia built into the system. And that's due to a variety of natural lags in the system. One, species migration can be limited by dispersal mechanisms. Seeds just can't really travel that far. The rate that trees mature to become seed-bearing, or any other plant becomes to become seed-bearing, that requires some time. There can be limitations to how well a plant species might be able to colonize a new site. There might be soil limitations to that. That alpine that's transitioning to cold montane forest, you might actually have to wait for some soil development to happen before it could support the cold montane forest. And then we know that trees, in particular, happen to be pretty long-lived, and they may sit there on a site for a long time, surviving whatever climatic conditions they're subjected to, when their seedlings and their offspring don't fare so well. So those trees stick around for a long time, even though their children won't. And so it's best to view these maps and these chord diagrams as like, this is the climatic suitability for a vegetation type. It's not predicting the vegetation type. But it's a good mental model to use so that you can try to anticipate what's going to happen. And then finally, this disturbances, we also know, can mix things up quite a bit. So even though there's a high degree of inertia in the system that I just described for a variety of reasons, there is also the potential for high mortality disturbances really catalyzing abrupt, rapid change. And that's what we have with fire. So how might vegetation change? Well, definitely away from our reference period conditions. We need to expect that it's going to change. And generally speaking, it's going to trend toward climate, toward vegetation associated with warmer climates. Big surprise there. Some additional caveats and assumptions that we need to acknowledge here are that each of these global climate models comes with a set of assumptions. The emission set of scenarios come with a lot of assumptions that we're going to continue business as usual, or maybe we're not. Land fire data has its own assumptions associated with it. This analog approach also misses the details. It misses some mechanisms that are in some of the processes there. With increased CO2 in the air, we might have a fertilization effect where plants actually become more efficient with the way they use water. There's a whole host of things that a process-based approach, a process-based model would be better at, but it would be hard to do for so many large areas like we were able to do with this approach. We used a really simplified characterization of climate. We distilled it down to these two water balance variables. And we did it on an annual basis, right? These are annual metrics. So that ignores any, seasonal influences that might be in there. Still, they're pretty good. Other people have found that these are two very good variables for looking at vegetation change. But the major assumption, I think, is that that you have to keep in mind is that this assumes that vegetation, these maps, if you look at those maps, it assumes that vegetation is able to keep pace with climate change. And it ignores those lags, and it also ignores things like human influence, replanting, suppression, and so forth. And we don't explicitly address the fire-climate feedbacks that might occur, which we've been convinced are highly important. So interpret them as maps of climate suitability. Focus on the direction of change rather than the magnitude or the timing.